Okay, so I think I'm going to start this guest lecture of reinforcement learning. So hello everyone. I'm a third year PhD student in the machine learning research group of the computer science department, and I'm also a GTA for this class. My research focus is on reinforcement learning, and today I will give a guest lecture on reinforcement learning to you, just to try to provide you with a general understanding of this area. Please see that this is just a guest lecture and will not be included in your exam. So this lecture has 4 major sections. In the first section, I'm going to talk about some basic knowledge in reinforcement learning. Then in the second section, I will introduce a few classic reinforcement learning algorithms. After that, I want to share with you some more advanced and important concepts in reinforcement learning. And finally, we will look at a few popular state-of-the-art reinforcement learning algorithm examples. Please see that I may have a bit more equations, but please try to focus on what I'm trying to show you and the implications behind all the math. You don't really have to totally understand every equation now. You can look at them more carefully afterwards, and I assure you it will not be very difficult. If you have any question, please feel free to interrupt me, and I will be more than happy to discuss them with you. So before we start on the basics, I would like to show you around the history of reinforcement learning. Before the contemporary reinforcement learning comes into being in around the 1980s, there were 3 historical threads. The first one is learning by trial and error, which originates from animal learning psychology, where animals learn through receiving stimulus or reinforcers from their environment to guide them on how to behave better next time. The second thread is optimal control, where people work to optimize a dynamic system's behavior over time. The third one is temporal difference learning, which utilizes the intermediate estimations during learning. In the mid-1980s, deep reinforcement learning started to get more attention because of the rising interest in neural networks. Starting around 2012, there is a revolution on deep learning, which led to a renewed interest in deep reinforcement learning. Later in 2013, deep reinforcement learning started to show impressive results in many applications. In this next slide, I want to share with you 2 famous applications of reinforcement learning. On the left side, we have AlphaGo, if you know that, which was published on Nature in 2016. It applies Monte Carlo tree search to play the 2-player competitive game of Go using a policy network and a value network. It achieved superhuman performance, which was very popular at that time. The policy network is firstly trained by supervised learning with human knowledge, then trained with self-play reinforcement learning. The value network is only trained with self-play reinforcement learning. Self-play learning means learning by playing a policy against itself. We will explain in detail about what the policy network and the value network are in later slides. This work also gave an initial explanation on its superb performance. With only supervised learning, the agent can only mimic the human performance without a way to surpass it. But with self-play reinforcement learning, the agent plays against itself without any restriction from expert demonstrations. So that's basically what they explained, how reinforcement learning get that superhuman performance. On the right side, we have ChatGPT, which is a very famous recent work. The 3 major steps in its training process are: firstly, train a policy with supervised learning, then train a reward model also with labeled data. The last step is to optimize the trained policy from the first step with PPO reinforcement learning algorithm and the trained reward model. The trained reward model from the second step. So PPO is a recent reinforcement learning algorithm with very good performance. We will introduce it as well as what a reward is in a later section. Basically, a reinforcement learning is a process of learning by trial and error. In a reinforcement learning task, we will firstly have a learning agent here who learns and maintains a policy, which is basically a strategy that the agent relies on to make action decisions. When the policy has chosen an action here, under the current environment state, the agent will perform it in the environment, which is this part, and then receive a reward here from the environment, which shows how good the environment thinks the previous action was. Then the environment will transition from the current state to a next state. With all this information, the agent will use his algorithm to update his policy and gradually learn to make better action decisions. So now we've generally described the whole reinforcement learning process. Next, I want to talk about some important basic concepts in RL through an example task called card pull, which is this simple one, a simple control task, where the agent takes actions to try to keep the pole in an upright position. So before we dive into the details, let's first look at a state series of the card pull control task. From the first state here on the upper left corner to the last state on the lower left corner, following the directions of the red arrows. In the first state, the pole is leaning towards the right side, if you can see, slightly leaning towards the right side. And then following the agent's decision, we push the card a bit to the right. Then because of inertance, the pole will then return to the upright status, showing in this state 2. And then the pole again falls towards the left side. And now we push the card a bit to the left, and it again returns back to the upright status. Then we will be looking at those basic concepts of reinforcement learning one by one. The first basic concept we're looking at is the state space, which contains all possible states that an environment could be in. For the case of card pull, an environment state at a certain time step is a 4-dimensional vector. The first entry describes card position ranging from minimum -4.8 to maximum 4.8. The second entry describes card velocity from minimum velocity from minimum minus infinity to maximum infinity. The third entry is pole angle from minimum -24 degree to maximum 24 degree. The last entry describes pole angular velocity ranging from -infinity to infinity. The next one is action space, which contains all possible action choices an agent has in the current task. In this case, action A under the current time step is a 1-dimensional vector with values of either 0 or 1, with 1 meaning pushing the card to the left, with 0 meaning pushing the card to the left, 1 meaning pushing the card to the right. Then here comes the policy. It is basically the strategy that the agent follows when making action decisions. it will give a proper action under a certain state. A policy is usually probabilistic, but sometimes can also be deterministic, compared to a deterministic policy which gives exactly one action choice under a certain state. A probabilistic policy will give each possible action choice under the current state a probability. A higher probability means that the policy is more confident about this action. It thinks the action is very good. We know that a reinforcement learning environment has a set of state transition probabilities, which describe the possibility of transitioning from a current state ST to a next state ST plus one. This first expression shows the probability of transitioning to a next state ST plus one is only relevant to the current state ST regardless of all previous states, which is called a memoryless property, which is a major property in Markov decision process. Hence, the reinforcement learning process is often modeled as an MDP, a Markov decision process. Then this second expression expands the probability to be the weighted sum of all the probabilities of transitioning from a current state ST to a next state ST plus one over all possible action choices under the current state. The weights are the policy probabilities, which is this one measuring the possibility of selecting certain actions under certain states. Then this expression of P means the probability of performing the action A under the current state ST and then transition to the next state ST plus one. Then we will be looking at a reward function, which is a very important part of any reinforcement learning task. It is part of the environment and it gives rewards for actions that the agent has performed under certain states. This R here refers to the reward that is given to the agent to assess his decision of performing action A under current state S, then transition to the next state S prime. This whole probability here refers to the probability of transitioning from a current state ST to a next state ST plus one after performing an action AT. So this entire last equation here is basically computing the expectation of the current reward RSA. A higher reward means that the action is very good, which is just the objective of the whole learning process, to try to always choose actions that will receive high rewards. The last two important concepts are values. Let's first look at the state value, which measures how good a state is in the long term. But what does that mean? So let's first look at the expressions of state value. The first one here, which shows that it is the discounted sum of all rewards that the agent is going to receive in the future towards the end of the current episode. To explain the concept of an episode, for example, if a reinforcement learning agent is playing a game, actually this card pull task can also be viewed as a game. So an episode means one round of a game. It ends when the player fails or he reaches the end state of a game and finishes. Further, through getting this discount factor gamma here out of these parentheses, we can express the state value in an iterative way as a Bellman equation here, which is this last equation. As we've discussed in the state transition probabilities, the possible next state after the current state ST can't be randomly anything, but rather is limited within a specified state set. There will be probabilities of transitioning from the current state to a next one. So when we say a state has a high state value, we mean that this state is very good, and after this state, there will probably be a lot more good states following who also have high state values. So this is just what an agent is learning for, to try to always bring good states under which he could more possibly receive high rewards for his actions. Okay, so now we've mentioned the concept of Bellman equation. Here, I would like to discuss more about it. It is named after the man Richard Bellman who invented it. So this is a picture of him. He is also known for dynamic programming, curse of dimensionality, linear search problem, etc. A Bellman equation is basically, it basically breaks a dynamic optimization problem into a sequence of simpler sub-problems. Let's look at this series of equations. So as mentioned previously, a state value can be expressed in the form of this first equation. The state value is the learning objective or optimization target of the reinforcement learning process. With the idea of Bellman equation, we can decompose VST into the sum of the current reward, which is this R t plus 1 here, and a discounted next state value, gamma times VST plus 1. Hence, we can come into this first expression. Further, the next state value, VST plus 1, can also be decomposed into the sum of its current reward, which is this one, and its discounted next state value, gamma times V t plus 2. Then we will get this second equation. And then we can go even further, decompose VST plus 2 to get this third equation here. Okay, so I wish now we've had some basic understanding of this iterative nature of a Bellman equation. And let's continue to the next basic concept in reinforcement learning. The other one of the two values is called action value, which measures how good a state action pair is in the long term. It is the discounted sum of all rewards that the agent is going to receive in the future towards the end of the current episode after taking an action under a state, and it can also be expressed in an iterative way as a Bellman equation, just like before. And there is a direct relation between the state value and the action value, which is shown here. Basically, the state value can be expanded to be the weighted sum of all the action values over all possible action choices under the current state. The weights are the policy probabilities, which is this part, measuring the possibility of selecting certain actions under certain states. The concept of action value is similar to the previously discussed state value in terms of that they both measure how good something is in the long term. The difference is that a higher action value for a state action pair means after taking a certain action under the current state, there will probably be a lot more good state action pairs to follow. A state action pair means the decision of taking the action under the state. And if that's a good decision, the agent will very possibly receive high reward for that, which is just the whole learning, which is just the goal of the whole learning process. And here I have a table to compare the three types of machine learning from 5 different aspects. I would like to start with the one that I think is the most important and most commonly used when we distinguish supervised and unsupervised learning, which is the labels that correspond to this red row here. So we've learned that in supervised learning, the labels are completely known at the start of training, while for unsupervised learning, there are absolutely no labels. In reinforcement learning, the labels are the learned state or action values, which are learned from scratch without any prior knowledge. Then let's continue from the first row onwards. Firstly, what knowledge is it that the agent is learning? For supervised learning, it is a mapping from data to labels, while for unsupervised learning, it is the pattern in the data. For reinforcement learning, we're trying to learn a policy to guide the agent's action decisions and a value function, which is a mapping from states to state values for state value function, or state action pairs to action values for action value function. Then regarding the availability of data in both the supervised and unsupervised learning, the data are completely ready at the start of training. But in reinforcement learning, the data are the states and actions that are generated as learning goals. They're not ready at the start of the learning process. For the next one, the learning objective of supervised learning is a most accurate mapping from data to labels. For unsupervised learning, it is a most accurate pattern in the data. The objective of reinforcement learning is a most accurate value function. The last one is the metrics that we use to evaluate the performance of the reinforcement learning methods. As we often see in supervised learning, mean square error and mean absolute error are commonly used, while for unsupervised learning, we can use compactness or separation. In reinforcement learning, we look at the total return per episode to determine the performance of the reinforcement learning method. By return, we mean the accumulated rewards so far in the current episode. Then besides, I would like to supplement a few points to the table. Firstly, the learning of the policy can be integrated into the learning of the value function. When we've learned a value function, we can basically infer the policy from it. The policy can just be a greedy policy that always selects the action that has the highest action value under the current state. Then the next point is that the rewards that are given by the environment in the reinforcement learning process contain some information of the value labels and are used to assist learning. Finally, we conclude that the major difference of reinforcement learning is that the labels are learned from scratch. Okay, so in the next section, we're going to look at a few classic reinforcement learning algorithms. Q-learning is the most classic and one of the first reinforcement learning algorithms. It maintains a Q table to keep track of all the Q values and it keeps updating the table till convergence according to its update rule. The rule first calculates the difference between the current Q value, which is this one, that is going to be updated, and its iterative expression, which is this part. The iterative expression basically expands the current Q value to be the sum of the current reward R and the discounted best next Q value, which is the highest possible Q value under the next state. Then after applying a learning rate alpha, this difference, which is this entire part, is added to the current Q value to update it. Then let's look at SARSA, which is another reinforcement learning algorithm that uses a similar update rule, just that it replaces the best next Q value here with this one, which is the Q value of the real next state action pair. Then double Q learning is an improvement over the original Q learning algorithm, which maintains two Q tables to avoid value overestimation. It modifies the update rule of Q learning to consider both tables while updating each one by firstly finding the action that gives this one, which is this one, that gives the highest action value under the next state in the current Q table. And then using the action value of that action with the next state in the other Q table, which is this one, to replace the best next Q value in the original update rule. So basically this cross usage of the two Q tables is the major contribution of this work. Later, when deep learning becomes more popular, people apply deep neural networks to replace the tables, called the DeepQ network. These Q tables can take raw RGB images as input, use a replay memory to store data to be sampled for training. The form of the loss function is shown here, which is the square of the distance between this YT and this current Q function. Here, phi t is a pre-processed version of the state ST, and theta t represents the network of parameters. YT expressed as being the current reward R for terminal states, or the iterative expression, this one, for non-terminal states. This iterative expression is it expresses the current Q value. Here, it instead uses a target network to find this one. The target network has parameters theta t dash. It uses the target network to find the best next Q value. This target Q network is a more stable version of the Q network whose parameters get copied from the Q network every constant number of steps. This constancy is set as a hyperparameter. Then in the final part of this section, I would like to discuss two improvements to the DQN method. On the left, the double DQN method introduces the idea of double Q learning into DQN. It maintains two deep Q networks to be used interchangeably in their update process, and actually uses the target network as a second Q network. Accordingly, it modifies the expression of YT for non-terminal states by changing the best next Q value in the same way as double Q learning. And basically, it firstly finds the action that produces the highest Q value under the next state through the current Q network. Then finds the Q value of that action with the next state through the target Q network, which is this entire part, and uses this Q value as the best next Q value. On the right side, there is the prioritized replay method, which assigns a priority to each experience in the replay memory. By an experience, we mean one piece of data containing the current state, which is this part, the current state action, the received reward, and the next state as shown in this expression. It assigns a temper difference error delta here to each experience, and then adds a small constant to it to get PI, which is the priority of each experience. After that, the method will calculate a probability, which is this capital PI for each experience over a mini batch of experiences, and use these experiences for training according to their probabilities. Okay, so we have discussed some basic concepts in reinforcement learning in the first section. In this section, I want to further introduce a few more advanced concepts. I will present them in pairs to try to help you gain a better understanding through comparison. The first pair is the concepts of value-based method or actor-critic method. All the previously mentioned algorithms that belong to the value-based methods. These methods learn value functions and then select actions according to the value function. Through, for example, a greedy algorithm. A greedy algorithm makes decisions only based on the current information for a local optimum without any consideration about the future. In comparison, the actor-critic methods learn both the policy and a value function, then directly use the policy output as action decisions. Here, I present the common form of the policy gradient, shown here. Sorry. this one. And we have a new concept here called the advantage function, which is the difference between the action value and the state value. And the following expression is a further expansion of this advantage function. It expresses the Q value in an iterative form. The next pair is the tabular or approximate methods. The tabular method uses a table to store Q values and update the values in the table as learning goes to convergence, while the approximate methods use a function to map states to state values or state action pairs to action values. And recently, due to the prosperity of deep learning, people started to use deep neural networks to replace normal functions. The third pair is a concept of model-based or model-free algorithms. By model, we mean the environment model, which includes two parts. The first one is a reward function. The second one is a environment transition dynamics. Model-based methods are based on the condition that the two pieces of environment information are already known, and then they may apply techniques like dynamic programming to solve the learning problem. However, the other one, which is the model-free algorithms, are the more common type of reinforcement learning algorithms. They work in unknown environments, receive rewards, and perceive environment transitions as learning goals. This pair may be a bit harder to understand, but is very important. Before we talk about on policy or off policy, we should first know two basic concepts: a target policy or behavior policy. The target policy is a policy to learn, while the behavior policy is a policy used to guide action decisions during learning. If the two policies are the same one, then the algorithm is on policy. Otherwise, the algorithm is off policy. I think it's better to explain them with examples. As we've learned in the second section about Q-learning and SARSA, SARSA uses the same action that was selected in the learning process in its update rule. In this case, the behavior policy is the same as target policy. Hence, SARSA is an on-policy algorithm. For Q-learning, it uses an epsilon greedy policy when selecting actions during learning, but the target policy is absolute greedy. Hence, Q-learning is off policy. Then this is the last pair, which is about Monte Carlo method or temporal difference learning. A Monte Carlo method relies on repeated sampling. It may generate a complete trajectory for each episode, and then sample data from it for training. Reinforce is a typical example algorithm of this type. The other concept contrary to that is temporal difference learning. This type of methods makes updates during the ongoing episode with intermediate estimations. The Q-learning and SARSA algorithms are two typical temporal difference learning algorithms. Okay, now we've gone through all the basics of this lecture. This is going to be the last section, and we will be looking at a few very popular state-of-the-art reinforcement learning algorithm examples. So PPO, if you remember, we mentioned that algorithm previously. It is a popular recent algorithm that has very good performance. It is used in famous applications such as ChatGPT. The major novelty in PPO is a new clipped surrogate loss for the policy function. If we consider the loss as a function of R, which is this thing, the R is a ratio of the current policy to the previous policy. The value range of the loss function is shown in the two figures on the right side. Through this clip function, R will be restricted within the range of 1 minus epsilon to 1 plus epsilon, where epsilon is a small constant. Then the loss is further restricted between the two dashed lines in the two figures. Just like this. To explain it in an intuitive way, this clipped surrogate loss is a lower bound on the original loss. The purpose is to try to penalize too large policy update. And another interesting algorithm is called PPG, which alternates between a policy phase and an auxiliary phase. The policy phase does normal PPO training. The auxiliary phase optimizes a modified joint objective for the policy network, which is because this algorithm adopts a new policy network architecture with an additional output of the value function here. Basically, in addition to a KL divergence here between the previous policy and the current policy, the joint loss has an auxiliary term, which is the distance between the value function approximated by the policy network and another estimated target state value function according to the methods introduced by reference 2 and 3. Here beta colon controls trade-off. The target value function, this thing, it basically used to guide our learning of the value function. And while the KL divergence is used to limit each policy update to stabilize training. Then this one, A3C, it is basically a distributed training framework. It does not have too much math in it. It is published in 2016, which is kind of very popular then. It maintains a central copy of neural network model and multiple workers. The workers do environment interactions, calculate gradients, and send them to the central model asynchronously. The central model apply the gradients when receiving them, then the worker periodically retrieves model parameters from the central copy and synchronizes local model parameters with remote parameters. Then the next work is called ACER. It has 4 major innovations. The first one is that it adopts the method in reference to in its Q-value estimation process. We don't really have to understand this long equation here, but we can only know that the Q value and V are estimates of action value or state values, and then the Q-ret this thing will be utilized in the update process of the Q function. Secondly, it adds a correction term which is weighted by a truncated importance weight to the gradient expression to bound its variance. The third one is that it maintains an average policy network that represents a rounding average of past policies and forces the updated policy to not deviate far from this average. And finally, it proposes a stochastic dueling network architecture, which outputs a stochastic estimate of Q-value function and a deterministic estimate of state value function. And now here comes our last algorithm, which is called TD3. It applies the idea of double Q learning to avoid value overestimation. Explicitly maintains an actor network and 2 critic networks Q theta 1 and Q theta 2. And then it modifies the expression of YT, replacing the best next Q value with a smaller one of the 2 next Q values from the 2 target networks of the 2 critic networks. This way we can have the YT being the same for both of the 2 critic networks. Then theta phi and theta prime and phi prime are parameters of the target networks, S prime is the nexus state. Here epsilon is a small constant that follows a clipped normal distribution. Lastly, it delays the update of policy network and its target network until a number of critic updates are performed to avoid high variance in policy updates. Okay, so now we've finished the last section, and I want to conclude it a bit. If you have the impression we've come across the idea of stabilized training many times in different algorithms, often by limiting the size of each update. Even though they adopt different approaches to do this, the goals are the same, which is to avoid updates that are too big to be reliable, which should be something very interesting that is worth thinking about from my point of view. Okay, so that's the end of this lecture. If you have any questions, I would be happy to discuss them with you. So otherwise, that's the end of today. Thank you.